A spherical snowball is melting at a rate proportional to its surface area. The surface area of a sphere of radius r is 4 pi r squared. The volume is 4/3 pi r cubed. Now, since it's melting, its volume is decreasing, of course. So the change in its volume with respect to time is negative. So when we say the rate of its volume is decreasing, we mean the rate with respect to time, of course. So time is the independent variable here, even though it's not mentioned explicitly in the question. So for a given tiny increment of time, dt is some positive number because we consider time to be always increasing, the change in the volume will be negative. The change in the volume is the initial volume minus the final volume over a small increment of time. And the initial volume is greater than the final volume, since the snowball is melting, since the volume is decreasing. So anyway, this derivative is negative. We're also given that this derivative is proportional to the surface area. So if one quantity is proportional to the other quantity, it means that if we double one quantity, we will double the other quantity. Or if we multiply, say, this by any value, we will have the effect of multiplying the other side by the same value. We can write this proportionality relation as an equation by setting dv dt equals a constant times the surface area. So c is some fixed value. It doesn't change with time. I'm calling it c. I'll write it like this, 4 pi c r squared. So that's how we turn a proportionality relation into an equation. We just multiply one side by a constant, whatever the constant is, to make both sides the same. We don't know what it is yet. As a matter of fact, we probably don't have enough information here to find out what c is. Okay, let's look more closely at dv dt. Here's the volume as a function of the radius. So let's plug that in. So we want to look at the derivative of this expression here. Well, the 4/3 pi is just a constant, so we can take that out. It's just a constant multiplied by r cubed. Now we need to look at the derivative of r cubed with respect to time. Now we don't know what r is as a function of time. We don't know how the radius is changing with time. Well, except we know that it's decreasing, of course, but how it's decreasing we don't know. Here's dv dt up here. But let's rewrite this. Whatever r is, if we take its derivative, we get 3r squared times dr dt. That's if we take the derivative of r cubed. We can just use the chain rule to do that. So we have the derivative of some quantity raised to a power. So we deal with the power first, take the power in front of the bracket, subtract 1 from the power, as if we know what the r is as a function of time. And the next step in the chain rule is to actually differentiate what's inside the brackets with respect to time. So we just write that as dr dt, since we don't know what r is as a function of time. Now, this enables us to actually get dr dt. So what happens here actually is that r drops out of it. So dr dt is a constant, doesn't depend on r. Simplifying further, dividing both sides by 4 pi, the 3's cancel here, we see that dr dt is actually equal to c. But of course, c, as we said earlier, is the constant of proportionality. So we've proven now that dr dt is a constant and is equal to the constant of proportionality for this equation here. Now another thing about dv dt is that it's negative, as I said earlier, so this has to be negative. R squared, however, is positive. 4 and pi are positive numbers. So this tells us that c is a negative number. C must be negative. And that makes sense. dr dt has to be negative because the radius is decreasing with time. The radius has to be decreasing if the snowball is melting. So for a given increment of time dt is some positive value, the change in the radius will be negative. The change in the radius is the initial radius minus the final radius. The initial radius is greater than the final radius, so that difference dr will be negative. So of course this quantity here overall will be negative. If the snowball loses half of its volume in an hour, how long more will it take for it to melt completely? Well, let's look at the volume at time 0. The volume is given by 4/3 pi r cubed, of course. But, you know, if we know the radius at time 0, I'll write it as r at 0, then the volume is 4/3 times pi times r at 0 cubed. We'll get back to an expression for r of t soon. Now, we're assuming here that t is in hours. The snowball loses half of its volume in 1 hour. Let's first of all look at v at time 1. Well, that's r at time 1, 4/3 pi times r at time 1 cubed. But it's got to equal half its initial volume. That's half of the volume at time 0, which is given by half of this, of course, which is 2/3 pi r at time 0 cubed. Next, we can get the relation between the radius at time 1 and the radius at time 0. That is the radius after 1 hour and the radius initially. So we can divide both sides by pi, multiply both sides by 3. Now for convenience, instead of writing r and 1 in brackets, I just write r subscript 1. So 4 times r1 cubed is going to equal 2 times r0 cubed. I write this r of 0 as r subscript 0. So now at last we can get r1 in terms of r0. So I divide across by 4, we get r0 cubed over 2, take the cubed root. So we see that the radius after 1 hour is the initial radius, r0, whatever that is, divided by the cubed root of 2. Now it seems that we don't need to know what r0 is, it could be any value. The answer is independent of r0. Next, we're interested in the relationship between r and time, how r decreases with time. So we go back to this equation from the first part, and we can rearrange this and integrate to get r as a function of time. So multiply both sides by dt, integrate both sides. Now if we integrate dr with respect to r, well, we're actually integrating 1 with respect to r. You could think of it like that. That'll give you r. And if we integrate a constant with respect to time, well, that's just a constant times time. So if the constant is 5, if we integrate 5 with respect to time, we just get 5t. But of course we get another constant then, because these are two indefinite integrals. Now I'll call the other constant e. E is yet to be determined. So if we differentiate this expression, if we work out dr dt, we're going to get c plus 0, because e is some arbitrary constant, its derivative is 0. So we'll end up getting dr dt equals c, and that's what we want if we take the derivative. Now let's consider the radius at time 0, like we did before. We just plug 0 in for t, and if we do that we get e. So this constant e is actually the radius at time 0. It's actually the initial radius, and we can write r at time 0 as r sub 0. So I sub r0 back in for e. Now we also have the radius at time 1, which is just r sub 1. So we plug 1 in for t, so we get c times 1 plus r0. And we know that this must equal r0 over the cubed root of 2. So from this equation we can actually get c in terms of the initial radius r0. C times 1 is c, and it's going to equal r0 over the cubed root of 2 minus r0. Finally, I can write r as a function of time in terms of r0. So I can plug this expression here in for c. So I can get r, remember, which is a function of time. I won't bother writing in t in brackets. So for c we have this expression here. So this is what we end up getting. So if we know the initial radius r0, we can work out r at any time t. We just plug in for t. We're interested in the time taken for the snowball to melt completely. When the snowball melts completely, the radius of the snowball will of course be 0. So we want the time for when R is 0. So we just set this equal to 0. So what do we get for t? Well, we bring the R0 over to the other side. It becomes minus R0. And we divide by the coefficient of t, which is this thing in here. Notice that we can divide above and below by R0. If we divide above by R0, we get minus 1. If we divide below by R0, we get 1 over the cubed root of 2 minus 1. So we get a value for t. So I've just changed the signs above and below. So on top we have 1, and we have to divide that by 1 minus 1 divided by the cubed root of 2. So this is what we have, and we want this to the nearest minute now. Time is in hours. That's the way we set up this problem. So to 2 decimal places, this is 4.85 hours. To the nearest minute, this is 291 minutes. By the way, this is the total time it takes for the snowball to melt, but we want to know how long more after the first hour will it take for it to melt completely, as half its volume is gone in 1 hour. So we have to take 1 hour from this, take 60 minutes from this. So the answer to the question is 231 minutes.